Hello everyone, I welcome you all in the third lecture of week 4 of the course Process Equipment Design, and here we are continuing the discussion on design of shell and tube heat exchanger using Bell's method. So if you remember the last lecture, there we have started Bell's method, and Bell's method is basically initially considers tube bank which is ideal in case. Okay, what is the meaning of that? What is the meaning of that? It means that no other factor is available and heat transfer is occurring over the tube. It means at the outer periphery of the tube, right, which will be in shell side of course. So once I am having that ideal case, the ideal case shell side heat transfer coefficient, we will further consider different factors. So we have already covered Fn factor, which is the factor for tube row correction. Okay, how many tube rows are available between baffle tips, that factor we have already considered in the last lecture. So continuing the Bell's method, we will first focus on window correction factor in this lecture. So let us start discussion on FW, that is window correction factor. So as you all know that in shell side the window is basically between baffle tip and shell diameter. Okay, so that gap which is available after baffle, the gap which is available after baffle cut, that we consider as window correction, and its effect is counted in Bell's method through FW factor. So window correction factor, when I am speaking, it is applied. So window correction factor, if I am considering, it is applied for the effect of flow through baffle window zone. Okay, so baffle window zone, what it is, that I have already explained. It is a function of heat transfer area in window zone and total heat transfer area. Okay, because some section of bundle is available in window zone also. So how much the area of bundle in window zone to total bundle area. Okay, so based on that we will consider FW. So based on that we will consider FW, that is window correction factor, and that factor you can simply see from this graph. Okay, here I am having FW, on y axis, and in x axis we have RW. So what is this RW? RW is the ratio of number of tubes in window zone to total number of tubes in bundle. Okay, so in this way we first consider RW and then we can find out FW. So let us see what is RW and how its value can be obtained. So let us see the calculation of RW. RW is nothing but ratio of NW and NT, okay, into twice, into 2, right. So what is NW? So what is NW? NT you know already, this we have used in bundle dia calculation, that is total number of tubes available in bundle, right. So NW is the number of tubes available in window zone. Okay, and why I have multiplied that by 2? Because between two baffle tips, okay, between two baffle tips we have two window zones. So 2 into NW by NT, that is basically the RW. So first of all we have to find out NW, because NT we already know. So how I can find out NW? That will be NT into RA dash. Okay, NW is NT into RA dash, and what is RA dash? RA dash is the ratio of bundle cross sectional area in window zone to total bundle cross sectional area. Okay, RA dash compare. So RA dash counts the area of bundle which is available in window zone to total bundle cross sectional area, and value of RA dash you can see from this graph. Okay. Now, if you focus on this graph, on y axis we have RA and RA dash, and on x axis we have cut, okay, and on secondary axis we have theta b, okay, and theta b is what? Theta b is the angle at the center of the shell which is made by baffle chord, okay. Now, here I am having both parameter RA and RA dash. RA dash you require over here, and if you see, if you need to use upper graph, you have to use this arrow as well as this arrow. It means upper graph will give the value of RA and RA dash, and below graph will give the value of theta b according to the cut. Okay. Now, the point is, RA dash we have already discussed, that is the area of window zone. RA dash we have already discussed that the area of bundle which is available in window zone to bundle cross sectional area, right. And if you see the y axis, there we have another factor which is RA. So, what is RA? RA is basically window area by total area. So, window area means that part of bundle as well as the empty area between bundle or the clearance between bundle and shell dia, right. So, RA and RA dash, if I am comparing its value we are obtaining from a single graph, but value should be different because one is the part of bundle and another is the part of shell, right. So, how I can differentiate between RA and RA dash? It will depend on what cut I am taking, okay. So, if I am saying that RA dash is the ratio of bundle cross sectional area which is available in window zone to total bundle cross sectional area, it means it is only counting the bundle, fine. However, RA is basically counting the shell, okay. So, to find out RA dash we have to consider the cut, and that cut is basically the bundle cut, okay. How you can find the bundle cut? It is very simple, HB by DB, okay. You have to consider bundle cut as HB by DB, okay, because HB is the section of bundle which is available in window zone, right, that we have already discussed in FN tube row correction factor, okay. So, that you can refer. So, here I am having cut which is basically the bundle cut when I am so, here I am having the cut which is bundle cut if I am considering RA dash, and if I am considering RA, the cut is of baffle cut, like you have considered 25%, 35% like that. So, based on different cuts you can use this graph. So, you should keep in mind that RA dash is a function of bundle cut. And what is bundle cut? That I have already explained. RA is basically the function of baffle cut, right. So, based on that you can find out RA dash, and then you can find out NW, and so you can find out RW. So, here I am having another parameter, that is NC. What is NC? NC is basically total number of tubes available in cross flow zone, okay. What is the difference between NCV and NC, if I ask you? NCV is basically number of tube rows, or we can say number of vertical tube rows in cross flow zone between two baffle tips, and NC is total number of tubes available in cross flow zone between two baffle tips. So, simply you can have this shell where I am having cross flow zone between two baffle tips, and these are basically NCV, and if I am considering all these values, so these are considered as NC, right. So, you should understand geometrically that what is the difference between NC and NCV, okay. And I hope you understand the difference between RA dash and RA and how to obtain that, right. So, once you have that RA dash, you can find out RW, and you can use the previous graph to obtain value of FW. okay, that is window correction factor. So, as far as window correction factor is concerned, it accounts, so as far as window correction factor is concerned, it is basically counted for heat transfer in baffle window, okay. So, its value is 1 for exchanger with no tubes in window, okay. Sometime window zone does not include any tube, and such type of baffles we have already discussed when we were discussing the constructional details of exchanger with shells, okay. So, there you can find the baffles of such type, okay. For other exchanger, it varies from 0.65 to 1.15, 0.65 for very large baffle cut to and 1.15 for small baffle cuts. For well designed exchangers, value of FW is usually close to 1. Okay. So, that value you can obtain from the graph we have already discussed, and accordingly you can consider window correction factor. Okay. Now, next factor is very important, that is bypass correction factor. Okay. Now, here we are considering basically stream C. If you remember different streams we have discussed in last lecture. So, FB basically counts different. So, FB basically counts stream C. So, first of all we will see what is bypass and how its effect can be reduced. Fine. So, you can see this is basically the bypass streams which we name as stream C also, and this bypass correction factor, it corrects for main bypass streams, okay, the flow between tube bundle and shell wall, okay, the flow between tube bundle and shell wall, wall, and is a function of shell to bundle clearance and whether sealing strips are used or not. Okay. So, what is sealing strip? Now, what will happen when I am having the bypass zone, there liquid will remain stagnant, okay, and liquid will not participate in heat transfer, and therefore, we avoid such accumulation of the fluid inside the exchanger, because exchanger is used to transfer the heat, and if stream is not participating in heat transfer, we have to make such arrangement so that it should come to the main zone, and main zone is the cross flow zone, right. So, what we have to do? We have to bring the liquid which is available in bypass zone to the cross flow zone. Okay. So, first of all you see this schematic where at the top we have this strip, right. We have this strip, and this is basically covering the bundle, okay. And if this is the shell and this is bundle, this basically covers this gap and distribute liquid from this clearance to main cross flow zone, right. And in this schematic, cross sectional view is shown where you have this bundle and this is the shell, and here I am having the baffle strips, and here I am having the sealing strips. So, sealing strips are nothing but the metal strips which is inserted in baffles to distribute the liquid which is available in bypass zone. Okay. In this image you can see the baffle, in this image you can see the sealing strips. This is basically the sealing strips, this is basically the sealing strip, right. This is also a sealing strip. So, sealing strips are basically inserted in the baffle, and this basically reduces this section. Okay. If I am not putting any sealing strip, then what will happen? This complete section remains available for liquid, okay, where liquid can be accumulated. So, if I am using these sealing strips, it distributes the liquid, because when sealing strips will be there, because the hurdle in the flow, liquid will be distributed and it will reach to the cross flow section. right. So, in this way we are using the sealing strips, and where sealing strips are most important to place when I am dealing with internal floating head heat, when I am dealing with internal floating head heat exchanger, right, because that is the only heat exchanger where clearance is maximum. If you remember the clearance curve, if you remember the clearance graph, right. So, in that case we should definitely use sealing strips. However, first of all we should check that whether sealing strips are required or not. Okay. For that also we have some criteria. So, let us discuss that. So, here I am having the expression to consider bypass correction factor, which is the function of AB and AS, NS and NCV, right, and alpha also. So, all these parameters you can see below. Alpha is basically the factor which is counting the flow. If turbulent flow is the, if laminar flow is there, we can have different value of alpha. For turbulent and transition we have different value of alpha. So, whatever would be the region that you can consider through Reynolds number, you can choose alpha value accordingly. And AB is basically the clearance area between bundle and shell. Okay. So, AB basically counts where stream C will lie. Okay. So, we will calculate that area, then only you can understand the necessity of sealing strip. AS is the maximum area for cross flow, because this is at the bundle equator. So, that is the maximum cross flow area as we have discussed in Kern's method, right. So, this AS you have to take directly from the Kern's method. Okay. Now, why I am considering AB and AS? AB is the area which is available between bundle and shell, right, and fluid or stream C is available there only. Okay. However, cross flow area, why I am taking? Because I am bringing stream C to cross flow area, so that it can participate in heat transfer, right, and should not remain at dead zone. Okay. And NS is basically number of sealing strips which will depend on the clearance. Okay. And finally, we have NCV, which is basically the vertical tube row restrictions, okay, that we have already discussed in FN correction factor. So, here we have the expression like FB is a function of areas as well as sealing strips. So, this sealing strips must have some maximum value. What is the maximum value? The maximum value of sealing strip should be equal to or less than NCV by 2, okay, because we are bringing the fluid to cross flow zone. So, we have to consider restrictions available in cross flow zone, and that is NCV. Let us say if your NCV is coming like 15, so you can consider maximum 7 sealing strips, and usually sealing strips are even number. If you are putting one sealing strip at top or the upper clearance, you have to put one sealing strip at bottom clearance also. You have to put another sealing strips at bottom clearance also, right. So, NS should be even number, and that should be equal to or less than NCV by 2. So, here you can see this schematic. So, AB is basically this area between baffle. So, AB is basically this area between two baffle, and it will depend on the clearance. So, we can find out AB like LB, that is the baffle spacing, DS minus DB. So, you can simply find out this section area. So, you can simply find out this section area as AB. AS you know already, so I am not going to explain that further. Now what you have to do? First of all, you have to consider whether sealing strips are required or not. Okay. For that, what you should do? You have this expression of FB, right. In this case, you will put NS as equal to 0 initially. Okay. You will put NS equal to 0. While putting NS equal to 0, you can find out FB value. Okay. If FB value is greater than 0.6, right, if FB value is greater than 0.6, we consider that no sealing strips are required. Right. And at ns equal to 0, if FB value is coming less than 0.6, here we should equate also, and if it is coming less than 0.6, it means sealing strips required. Sealing strips are required. So, we have two cases. First is you do not need sealing strip, and second is you need sealing strips. So, if you do not need sealing strips, okay, if sealing strips are not used, you should use this graph to see the value of FB. Okay. So, here I am having AB by AS. Depending upon the Reynolds number, you can find out FB value from this graph. Okay. Now, what will happen if I need sealing strip? Okay. In that case, you will consider different NS values. Okay. And as I have told you, NS value should be as I have told you that NS value should be even. So, we have to first check with 2 NS stream, 4 NS stream and 6 NS value, right. So, if 2 sealing strips I am considering, we have to find out FB at NS equal to 2, okay, and that FB value should be more than 0.85. Okay. Now, why 0.6 and why 0.87? Now, why 0.6 and why 0.85? This is basically the range which we are considering that FB should be in feasible range. Okay. So, that point we will further discuss. So, first of all, you have to put NS equal to 2 and calculate FB value, right, and you should keep on increasing the NS value in even number till FB becomes greater than 0.85, right. If you keep on increasing NS value, where you have to stop? You have to stop when NS should be equal to less than or equal to NCV by 2, and that value should be equal to, and that value should be even, right. So, you have to stop when FB value. So, you have to stop when FB value you can obtain as 0.85. So, first you have to check whether sealing strips are required or not, and then you have to obtain FB value accordingly, right. So, here I am having bypass correction factor. So, the bundle bypass streams around the periphery of tube bundle from one baffle window to the next gap between outermost tube and the shell, right. It is accounted by the factor FB, we have already discussed, and its value vary from 0.7 to 0.9. Therefore, I have chosen a range 0.6 to 0.85. Okay. So, lower value indicates the need to add sealing strips which force bypass streams back to the tube bundle, right, and therefore, we are considering the gap between bundle and shell and the cross flow area, right. So, resulting improvement in heat transfer is reflected in an increase in value of FB with the number of pairs of sealing strips. So, therefore, I have told you number of sealing strip. Therefore, I have told you number of sealing strips should be even in number, okay, but because that should be installed in pair. Okay. Next factor I am having is the leakage correction factor. Okay. So, this factor considers the leakage through tube to baffle clearance and baffle to shell clearance. So, if you see this schematic, leakage correction factor basically counts stream A and E, right. So, we have this correlation for leakage correction factor, which is basically function of beta L, ATB, ASB and AL. So, beta L is a factor, ATB is the tube to baffle clearance area, that is this section only, ASB is the shell to baffle clearance area, and AL is basically total leakage area where addition of ATB and ASB is done, right. So, ATB is basically CT pi D naught by 2 into NT minus NW. So, you see, as far as CT is concerned, that is basically the tube to bundle, that is basically tube to baffle clearance, and this difference or this gap is always 0.8 mm, right. So, CT value is equal to 0.8 always. So, here I am considering CT by 2 because I have to consider this gap only, okay, and pi D naught, that is the outer periphery of the tube. So, pi D naught into CT by 2 is basically the open section or the open periphery over the tube and between baffle hole, right. So, that should be multiplied. So, that should be multiplied by NT minus NW. NW is basically number of tubes in window zone, and this ATB basically counts tubes which are inserted in baffles, right. So, NT minus NW would be the total number of tubes which are inserted in baffles, fine. So, CT will be applicable there and value of CT should be equal to 0.8 always, right. And now we have ASB where CS ds into 2 pi minus theta b is considered, and that should be divided by 2, okay. And what is CS? CS is basically baffle to shell clearance, okay. Now, how I should find out this CS value? CS value will depend on shell dia, fine. So, you can use this table where pipe shells and plate shells are given, and you can have another factor, that is baffle diameter. Baffle diameter is what? Shell diameter minus some clearance. So, that clearance is basically 1 by 16 inches in pipe shell where diameter is in this range, right. So, 1 by 16 inches when you convert, it gives 1.6 mm. Similarly, for plate shell we can have same range of diameter, but clearance is more, okay, because plate shell is usually prepared with the rolling. So, more gap is usually kept for because plate shells are usually prepared with the rolling. So, some deformity may occur while rolling, okay, and therefore, smooth insertion, therefore, smooth insertion of bundle with baffle needs more space, right. So, in that case plate shell will have more clearance in comparison to pipe shell. So, the bracket which is available in this table, that you can consider as CS value. So, CS value by 2 because you have to consider the gap between baffle and shell, and ds is the shell dia. Now, 2 pi by theta b. 2 pi by theta b is what? Theta b is basically the angle which is made by the chord of baffle to the center of the shell, right. So, that theta b you can obtain from this graph. Here I am having the cut, and here you can see the theta b value, and in that case this cut will be baffle cut. So, you should keep in mind at which condition you have to use bundle cut and at what condition you should use baffle cut, okay. So, theta b will depend on the baffle cut. So, 2 pi, that is the complete periphery, minus theta b. So, it will basically give this section only, right, into ds, okay. So, in this way you can find out ATB and ASB. And once you know ATB and ASB, AL is the addition of ATB and ASB, AS is the cross flow area that we have already calculated in Kern's method. So, based on these factor you can find beta L, which is a factor, which is a design factor, So, considering all these parameters you can find out leakage correction factor, that is FL, okay. So, as far as leakage correction factor is concerned, it counts for both baffle to tube and shell to baffle leakage streams, okay. And as far as its range is concerned, the practical range of FL is about 0.2 to 1 with value 0.7 to 0.8 being typical. So, we should consider that value should lie between the value should lie between this. However, for well designed exchanger, FL should not be less than 0.6. So, if it is so if we are finding FL more than, so if we are finding FL less than 0.6, we should change ASB, ATB or beta L value. Okay. So, you should see what parameters will be affected when you have to increase FL or leakage correction factor. Further, the smaller values indicate the need for design changes to decrease the size of the leakage streams, that is increasing the baffle spacing. Okay. So, in this way you can consider FL factor and you can improve the parameter and you can improve the value of FL. Okay. And here I am stopping this lecture. In the next lecture I am continuing the design of shell and tube heat exchanger using Bell's method. Okay. So, that is all for now. Thank you.